My name is Mohammed Tarek, and today our discussion is on disjoint sets, or we can say union find data structure. Sometimes it is called union find data structure, sometimes it is called disjoint data structure. So I have used both the names for your understanding. Now, what is disjoint sets and how disjoint sets works? Before moving to this data structure, we need to first understand equivalence relations. Now, what is relation? This is a topic of discrete mathematics. So let's try to first understand how the relations works, and then we will come towards the equivalence relation in which we need to satisfy three conditions. So let's say we have two people here. There are two persons. We have a person whose name is Muhammad, and we have a person whose name is Ahmed. So Muhammad will be a part of some family, correct? And Mr. Ahmed, he also has a family. Right now, what information we have? We have only this information that Muhammad is a person and Ahmad is a person. We do not have any information about their families, their brothers, their sisters, their parents, their kids. So I can say that Muhammad is a part of, let's say, family one, right? And I can say Ahmad is a part of, let's say, family two, right? They both are members of their own families, and I've given family 1 to Muhammad and family 2 to Ahmad. So mathematically, I can say Muhammad is a part of set 1. There is an element in set 1, and there is an element in set 2, right? We have two sets, and we have single elements in those sets, right? Once we get further information, we can expand this set and we can add some elements in this set. Suppose we have a database of people. We want to figure out who is related to whom, right? Up till now, we do not have any any information related to relations. Now, initially, we only have a list of people and information about their relations. For example, Muhammad is related to Ahmed. Now we have information which is Muhammad is related to Ahmed. So now we have a relation between them, but what kind of relation it is? Are they brothers? Are they colleagues? Are they cousins? What kind of relation it is? So we know we know that we have a relation between two persons, or you can say between two objects, but we still don't have much information about that. Now we have information which is Muhammad is a brother. Muhammad is a brother of Ahmad, right? This means that they belong to same family. Mathematically, they belong to same set. Now we have some concrete information, and now they both are brothers, right? They both are brothers. So we can say that they both belong to the same family, right? They both belong to the same family. Now we have two elements. So this is, let's suppose this is family 1. We call them family 1. And mathematically we can say we have a set 1 having two elements, right? So in this way, when we have elements and when there is a relation between them, we join them or we group them in same set, right? Now let's see further. If Muhammad is related to Ahmad and Ahmad is related to Sam, then Muhammad is related to Sam. What does this mean? I'll explain you this point. Once we have relations information, we would like to answer queries like, is Muhammad related to Sam? So now we have three pictures. We know there's these both guys are brothers. And with additional information about Sam, we know that Ahmad is related to Sam, right? According to this information, Ahmad is related to Sam. And let's say they both are also brothers. They both are also brothers. So this will be correct to say that Muhammad is also a brother of Sam, right? Because we know Muhammad is a brother of Ahmad, and Ahmad has a brother with the name Sam. So I can extract this information, and this will be very true when I say that Muhammad is a brother of Sam. So in this way, we can extract information based on the relations, based on the information that we get. All three people, these guys are part of same family, right? Now we have family 1, and this family, mathematically we can say it's set 1 having 3 elements, right? So this kind of relation where we have one object is related to other object, and then the other object is related to the third one, and then we say the first object, which is Muhammad, is now related to Sam. Let me clear this a bit. We can say that when one object is related to a second object and the second object is related to the third object, so we can say, or we can also create a relation between first and the third object. This is called transitivity. We will learn about this in the next slide. Now, the equivalence relation. What is equivalence relation? A relation R over the set S is called equivalence relation if it has following properties. What are those properties? Reflectivity. For all element X is in the set S, X is related to X. Now, what does it mean? For suppose I have A equals to B, so I can also say that A is also equals to, sorry, A is also equals to A, right? This will be true. Yes, this will be very true. So every element, or if I say Ahmad is a brother of Sam, right? I can say Ahmad is also related or also has a relation with himself. So Ahmad is also related to Ahmad, and this will be true. So every element, every object has a relation to itself, and that relation is a true relation. That relation cannot be false, right? So this was the uh, first point. Now, second point is symmetry. If for all elements, for all elements x and y, x is related to y if and only if y is related to x. So now, for example, now I have these three pictures again. Now let's say this is x and this is y. So if Ahmed is a brother, Muhammad is a brother of Ahmed, so I can say Ahmed is also a brother of Muhammad, right? Will this relation be true, or will this statement be true? Yes, statement will be true. So this is called symmetry, right? This is called symmetry. For all element x and y, x is related to y if and only if y is related to x. So this condition is satisfied. Now the third condition, or the third point, is transitivity. For all element x, y, and z, if x is related to y and y is related to z, then x is related to z. So let's say we have x, we have y, and we have z. So if I say Muhammad is a brother of Ahmad and Ahmad is a brother of Sam, so I can say that Muhammad is a brother of Sam, right? Isn't it? So will this statement be true? Yes, this will be true. So when we satisfy all these three statements, or all these 3 points, all these three properties, we say that this relation is an equivalence relation, right? This is an equivalence relation. So, and this is based on the equality that one element, or you can say one object, is related to second object, and that is related to third object, and that is related to third object. So when these three objects satisfy these properties, then we say it's an equivalence relation, right? So now let's see what is not an equivalence relation. The less than relationship is not an equivalence relation. How it's not an equivalence relation? It is reflexive since x is equals to x is less than equals to x. So it is something like if I say a is less than equal to a, yes, because a is equals to a if it's not less than. Let's say if I say uh, 5 is less than equal to 6, yes, 5 is less than 6. Or if I say 5, and if I say 5 is less than equals to 5, yes, because 5 is equals to 5. Second point is transitivity. If x is less than equals to y and y is less than equals to z, so this implies that x is also less than equals to z. So now what does this mean? Let's say we have a is less than equals to b and b is less than equals to c. In this case, I can say something like this: 5 is less than equal to 6 and 6 is less than equal to 7. Is this true? Yes, it is true because 5 is less than 6 and 6 is less than 7. The transitivity property has also been satisfied. Now, what about symmetry? It is not symmetric since x less than y does not imply that y is less than x. So let's take same example. 5 is less than equal to 6. But if we revert this, when we will revert this property, the symmetry property, this will not be true because 6 is not less than and 6 is also not equals to 5. So less than equal to is not an equivalence relation. For further information about equivalence and relations, you can check on the internet or you can also refer any book on discrete mathematics. Okay, let's take another example. Electrical connectivity, where all connections are by metal wires, is an equivalence relation. When we have connections in using the electrical wires, that can be considered as an equivalence relation. Why? Because those wires satisfies all three conditions. For example, let's say I have these three wires. So I have these three wires. I have red wire, I have green wire, and I have black wire. And a current is flowing from red wire to the black wire. The current is flowing in this manner, right? So it is clearly reflexive since every component is connected to itself. So you can say that every component is connected to itself. So the current is going from red wire from here and now going out from this point, right? Going out from this point. It is symmetric because if component A is connected to component B, then B must be electrically connected to A. So as you can see, this red wire is connected to green wire. So it also means that this green wire is connected to this red wire, right? So this is also symmetric. The third point is it is transitive since if component A connected to component B and B is connected to C, then A is connected to C. So we can also label these wires as A, B, and C. So A is connected to B and B is connected to C. So we can say that this C is also connected to, we can say that this C is also connected to A, right? And this is true. Okay, now let's see how we can represent these relations. To represent these relations, we have a technique called matrix representation. Let's say we have Jack, Ali, Usman, Jamie, and Umar. We have these five guys, and these five guys have some relations with each other. Now, what is the relations between them? So let's say Usman and Ali, they are brothers, right? And Ali and Jamie, they are office colleagues. Okay, they work in same office. And Jamie and Jack, they are also brothers. And let's say Umar and Usman, they have a relation of teacher. Umar is a teacher of Usman, right? So we have these relations now. Now, how we can represent these relations? What I'm doing is I'm reusing this matrix representation. So if you remember the three properties we have, the first property is reflexivity. So every element or every person is connected to itself, right? If I say that Jack is connected to himself, or Jack is equal to Jack, so this will be true. This is called self relation. So I'm representing SR for self relation, or you can say the reflexivity. In the same way, Jamie is also related to himself. Umar is the same, uh, is in the same relation. Usman is also in the same relation, and Ali is also in the same relation. So this is the first and the basic property which has been satisfied, and all these guys are related to themselves. Now the second property we have is symmetry. So if one is a brother of others, then if we can say, then the first one is also a brother of the first one. So let's check this one, Usman and Ali. So Usman is a brother of Ali, and and Ali is a brother of Usman. So this satisfies the second condition also. So we can say that. So let me write true here. T for true, right? So in the same way, Ali is a colleague of Jamie, and the Jamie in the same way is also colleague of Ali. So Jamie and Ali, they are related. So Ali and Jamie. So this is also true. Now Jamie and Jack, they are brothers, and the same way Jack is also a brother of Jamie. So I can say, so I can write true here. Okay. So now Umar is a teacher of Usman, but Usman is not a teacher of Umar, right? So this condition is not being satisfied. So I cannot write anything on this matrix, right? Because this is not a symmetrical connection. So in this way, I can represent the relations in this matrix. So we only have five elements, you can say, or you can say we only have five people here, and we have a matrix of 5 by 5, right? We have a matrix of 5 by 5. But here is a problem. The problem is, what if we have 1,000 elements or objects or people? Now, how we can represent this relation in which we have 1,000 or more than 1,000 elements? Will this be efficient in terms of time, space, and memory to create a matrix of 1,000 by 1,000? Will this be efficient? And the answer is definitely no. This will not be very efficient. So, what to do to represent or to handle this kind of relations in which we have big number of data? So, to address this problem, I will discuss the solution in the next lecture. In the next lecture, we will see how we can solve this problem, and with that, we will try to create the data structure, the disjoint data structure, with the help of the solution. I'll see you in next lecture. Thank you.